What is Refills about? Refills is about developing novel mobile robotic systems that work in close and smart collaborations with the humans. And this allows addressing the main in-store logistics for retail stores, leading to a smarter shelf refilling in supermarkets.
When I'm looking into our distribution centers, then I recognize that we have a lot of technology in place there. But when we look into the stores itself, then we see that we have a lot of manual tasks without any automation support. And that was the starting point of Refills.
In the Refills project, we were looking at all conventional in-store logistics processes, all the way from shelf monitoring to store delivery to shelf refilling. Shelf monitoring mainly consists of data gathering processes, making sure the layout of the products on the shelf is correct, as well as the inventory of each product. When receiving new goods, the pre-sorting of goods in the backroom as well as the distribution of those goods to the shop itself are crucial. The shelf refilling is both a time-consuming and physically demanding process that is still completely manual. The Refills project aims at developing robotic systems able to address the in-store logistic needs of the retail market. 3 scenarios building on top of each other are considered. In the first scenario, mobile robots inspect shelves and generate semantic environment maps for layout identification and store monitoring. The second scenario employs robot arms for autonomous sorting of cases from mixed case pallets in the backroom, autonomously transporting trolleys from the backroom to the shop floor, and for assisting human clerks with shelf refilling. In the third scenario, research thrives to handle a wide variety of products and refill shelves autonomously.
The store management system from Swisslog, which is based on Swisslog Sync software, is the connecting software for all modules. For example, giving depalletizing cell carrier modules or trolleys or scanning and pointing modules a connection point. Each of these modules is individual, but the store management system combines all of these together to make the whole system working.
In order to build the semantic store maps, you first of all have to equip the robot with knowledge. The robot has to know how shelf systems are composed of their parts. So we have to tell the robot something like there is a base of the shelf system and that there are individual shelves, and the individual shelves are mounted at the shelf system in horizontally, and they are mounted at the back of the shelf, and that each shelf has separators and barcodes that basically tell which products are at that particular place. And then the robot has to take these informations and compute a plan on how it can recognize shelf system in a supermarket. So by doing that, it derives, for instance, that it first has to find the shelf system itself. If it has found the shelf system, it knows there should be individual shelves horizontally at different heights. So it scans the shelf bottom to top, and then it finds the individual shelves. And now it knows that in the individual shelves there should be separators and barcodes. So it basically scans horizontally to recognize, to detect and recognize them. And then when it knows which object is supposed at each facing, then it looks for the products itself. So the strategy of scanning can be derived from the structure that we have given the robot as a prior knowledge.
At Intel Movidius, we worked on identifying and counting the products on the shelves. In order to do this, the University of Bremen provided us with the 3D scans of the product to create a synthetic dataset for both product identification and counting. This dataset was then generated using Intel's Osprey renderer. We also created real-world dataset from DM Store in order to validate our product identification and counting methods in the real-world setting. For product identification, we start with the product image captured by the robot. Using AI, we convert it into a feature vector, which is essentially a sequence of numbers that identifies the content of the image. This feature vector is then compared with the feature vector of all the products in the database that we showed before to identify the correct product. Similarly, we use the state-of-the-art AI to look at the rows of the product on the shelves and count the number of products. Our AI is robust against other visible products in the image and densely packed products.
So semantic store maps are a very exciting representation of stores, because they are very realistic, they are very detailed, and you can look at them from different perspectives. So for one thing, you could take a semantic store map and have somebody kind of, when we render them in virtual reality, and simply go shopping in semantic store maps, right? Or you could also think of a system like a Siri agent, where you can just ask questions about the store, and the semantic store map could visualize the answers to these questions. So there are lots of applications that you can target if you have semantic store maps available.
Another module that was developed from scratch in the Refills project is the scanning module. Its purpose is to scan automatically the shelves with vision technology. And the platform basically consists of a retractable linear axis that can reach from the bottom level to catch the lowest shelf levels up to about 2.1 meters height to capture the products on the top level of the shelves.
The depalletizing cell is a new concept that combines a visual system with a new design of a mechanical gripper that allowed the depalletizing of heterogeneous pallets in a completely autonomous way. So without the intervention of any operator during all the process, from the identification of possible boxes to be grasped up to the delivery on a trolley or on what you need in your process. The new gripper that we developed is special because allows to adapt to different sizes of boxes and also allow possible grasps in different directions. For example, not only from the top, as is typical for other kind of grippers, but also lateral. So by grasping boxes from below, so in a way that if you have a heavy boxes or boxes that can be opened involuntarily, for example, if you grasp from the top, this cannot happen because you grasp by holding the boxes from below, from the below side. So this allows to have safe graspings for any kinds of boxes.
Within the project, we developed a carrier module, which is an autonomous platform developed to transport any module that we have in the scenarios from A to B. The carrier module was developed from scratch in the Refills project. In scenario 2, the collaborative shelf replenishing scenario, we added a pointing device which is helpful for untrained clerks to find the spot where they should fill in certain products. And it helps to speed up the whole replenishing process.
In the collaborative shelf refilling, heavy boxes have to be handled, and with our robot we are supporting the clerk with the critical tasks. The robot is handling the heavy boxes with pushing and adjusting them to a proper height for the clerk so that the products can be refilled by the clerk easily.
This robot places the case with the products at an optimal height and suggests the optimal refilling procedure from an ergonomic point of view. The system is tailored to the anthropometric characteristics of the specific clerk in order to reduce the risks of musculoskeletal disorders. To develop this system, we have carried out an ergonomic analysis of the refilling task by doing experiments and massive simulations using digital avatars. And we believe that the human-robot collaboration is meaningful only if it allows to improve the efficiency of the process by improving the working conditions and by preserving the health of the human workers.
So in the scenario 3 of the Refills project, the main objective is to try to perform the restocking process of products in a supermarket using a robot like this. One of the main challenges of this objective is the need to manipulate a lot of different objects.
We are able to combine visual and tactile sensors in order to do our in-hand manipulation maneuvers and correctly grasp the object on the pick tray and execute a pick and place task. We use the camera to detect the object on the shelf basing on artificial intelligence technique. Instead, we use the gripper and the tactile sensing to change the orientation of the object between the grippers. For example, let's take this object. We are able to change the orientation between the object and the gripper doing the so-called gripper pivoting maneuver. That means change the orientation of the gripper while keeping the object fixed in the space. Another in-hand manipulation maneuver that we can do is the dual one. It's the so-called object pivoting. We keep the gripper fixed into the space and we let the object rotate in hand so that to change its orientation. Both in-hand manipulation maneuver are model-based, so we don't use artificial intelligence on this kind of stuff, but we use only a model of slippage between the object and the tactile fingers.
And we combine that with our knowledge representation and semantic task specifications, and together we could go and basically place selected items at the right place in the right way into the shelf system.
For the autonomous scenario, the last link of the robot can be replaced by an actuated wrist. The wrist has 3 additional degrees of freedom and is equipped with a gripper so that single products can be manipulated. For that scenario, single products are standing on top of the trolley levels and they can be grasped by the robot and manipulated to the shelves.